Okay, so welcome everyone to uh, Optimal Control / Beluga course. Um, Today, we're mainly going to focus on parameter optimization. I assume that most people have learned parameter optimization, but it's necessary to build a foundation for what we're going to do later. And a lot of insight comes from the parameter world, and then we'll apply that to the dynamic kind of trajectory optimization stuff. So if I'm going to actually pull over, this is the front of the typed out notes I'm preparing. So these are the kind of the course overview. And then we have optimal control theory and Beluga. So we're going to alternate. So optimal control theory days are going to be the Wednesdays, and the Beluga days are going to be the Fridays. We're going to have parameter optimization, and then 2 days of optimization of dynamic systems, starting simple and then becoming complex. And then we're going to get really complex in the fourth lesson, doing control and path constraints and other things like that. And then the 5th day is going to do what are new techniques. And these new techniques are what enable us to do most of the things that we do with Beluga beyond solving simple problems. And on the Beluga cold days, starting this Friday and every other Friday, we're going to cover like the basics Beluga installation, the structure of Beluga, and like just general tips on Python. That's to help you start ready to use Beluga efficiently and then also contribute. I hope that some of you have the opportunity to contribute to Beluga as well as use it. We're going to then cover the initial guess and information and continuation methods, setting up problems in the storage path, going into the structure of Beluga in depth, and then discussing some open research in like ways that code could be improved, and also like if you're interested in more research topics, that kind of thing. So to start, for those who don't know, Beluga is a general purpose trajectory optimization suite. It's written in Python, and like all in Python, so that's nice with it. And then it's unlike other methods, like other solvers, I mean. So like those other solvers might be like GPOPs is one. There's also Dido. Basically any other thing that's labeled a trajectory optimization solver. Beluga uses indirect methods. And just as a side note, we are in the habit of spelling Beluga with a lowercase b. That wasn't my choice. That was actually like Mike Scarpani who did that. But I've got used to it too. So if you see Beluga spelled out, it will be with a lowercase b unless it's in the front of the sentence. And then we have, using indirect methods allows us to create high quality trajectories. So, and I'll get in more detail in the difference between indirect and direct methods later on. But it suffices to say now that when using direct methods, you can get often these like numerical artifacts that are not part of the optimal solution. We don't get those with indirect methods because we optimize the problem before we discretize it. That's it in short. Once again, I'll cover that more later, but that's like super general Beluga overview. So I hope you guys got that. Hopefully this writing paces things out. If it doesn't, I'm sorry. It's always pasted out to me. So let's think, okay, like what kind of problems can Beluga solve? So imagine we have the Earth here, and then we have some like glide vehicle coming in. It's coming in with some velocity, It's some like flight path angle, supposed to be a gamma, and we want it to hit some target here. So it has its states. Its states are altitude, latitude, longitude, and we also have a velocity, flight path angle, and then heading. So we have these 6 states. This is a 6-dot problem. And then we have controls. So controls, in this sense, are things that we can change. So we can change here angle of attack and bank angle. And then what do we want to do? We want to hit the target. So this is what we call an objective. It's also cost, but and I'll just describe in words here, is to maximize terminal energy, but at a cost that is like minimize negative final velocity. Okay, so we have this problem. So we want to guide this vehicle to this target. The things that we can dictate are the controls. So what Beluga does in a problem like this is we can put this in and we can find the controls that find the optimal. So like the path that minimizes the negative velocity by adjusting the controls of a vehicle like this. I'm not going to go any more in depth on this problem. This is just to motivate and kind of show what we're heading towards. We'll come back to this type of problem, and we could also, so like this isn't as complex as a kit can get. You could add more constraints like path constraints that constrain heat rate or G-loading or bound the controls and many other things. And yeah, we'll revisit this problem. But this is kind of where we're going, is being able to find the control histories that minimize some objective value. Okay, so now to the really fun part, kind of kidding, but the parameter optimization. So this is where we're going to start. So instead of that super complex problem, we're going to start with parameter optimization, which is non-dynamic. So by that I mean like everything is at a fixed time and everything's discrete. So yeah. The most basic class of these optimization problems. Sorry, my handwriting's getting a little sloppy. Is concerns finding some vector u of m parameters such that a cost j of u, this bar means it's a vector. I might forget it, so forgive me, is minimized. So, and then u is the control vector. Okay, so we'll write that kind of problem out as min with respect to u, j of u, right? And this should be pretty straightforward, right? It's just you apply calculus. So we have, so assuming if J of u has first and second derivatives everywhere. The necessary conditions for a local minimum are, then, so just remember calculus, right? So we have the first derivative with respect to u is equal to 0, and we have 1.1. And then also the second derivative with respect to u, and these are vector derivatives, so is greater than or equal to 0. That's 1.2. And then we could just, this is right here, this is positive semi-definite. Sorry, ran out of space there. So yeah, this is kind of simple review. But if we have some kind of function here, right, and let me change color, does this, right? At this point 1, that's a maximum, and then this one's a minimum. And we could tell that because at 1, the first derivative is 0, but the second derivative, so like the curvature, is negative. And likewise, the minimum, so this is 0, but then the second derivative is positive. For everything remaining in this course and any optimization you do with me, we only care about minimums, and that's because I think that's American. The Russians care about maximums. The problems end up being the same, but it's just whether you use a minus sign or not. So from 1.1, we get algebraic equations for our unknowns. So yeah, so we have u. So this is, unknowns, and that's a vector u. So we have equations to solve and get points, and those points are called stationary points. Okay. And these can be, and based on the second derivative, they could be maximum, minimum, or saddle points, which are neither. And if you look up, so when I said that these are necessary conditions here, that means that every minimum is going to satisfy 1.1 and 1.2, every local minimum. But there might exist some local minimum. If you just have 1.1 and 1.2, you actually can't prove that's a local minimum, because if the second derivative is equal to 0, that is a singular point. That's going to come up later, too. So more information is needed to determine the optimality of these points. So a good, just visual, quick example is you have something like this, right? And say it's up here, right? And then goes to 0, and then goes here. Here's a second, this is like a singular point here, right? But it's not a minimum. But we could also have something that is hard to draw, but you could also have something that second derivative is 0, but the third derivative and the fourth derivatives are not 0. So then that could be a minimum. Okay. And then if 1.1 and so if the second derivative is positive, definite, say this is 1.4, then you have, change that, sorry, insufficient conditions of optimality exist. So sufficient means that if these two are true, then you are guaranteed a local minimum. So that's the difference between sufficient and necessary. For the record, the rest of this course, we're just going to focus on necessary conditions. Sufficient conditions are kind of way too hard. And you're also going to, we're going to focus mostly on first derivatives and only in special cases second derivatives. So, but this is technically what you need. In the future, you could just use your engineering judgment to kind of guess, not guess, but to inform whether you meet the minimum. Okay, so now this is all super easy, but we move on. And then we to problems with equality constraints. So okay. So a more general class of optimization problem involves minimizing a scalar cost j of x used. So this time we added x, where so this is called a state vector. The state vector x. So that state vector contains n parameters determined by n constraint functions. So the constraint functions of this form. So the f of x u equal to, we can have many of them, so a vector and that's all equal to 0. Okay. So we write that as sorry, I'm skipping ahead in my notes. Minimize u, j of x, u, subject. So we minimize j over, with respect to u, subject to, then we have f x u is equal to 0. And I'll call that whole thing 1.6. I'll reference it later. And at this point, so is there any questions? Is everyone hearing me fine and following?
Yep, I'm hearing you and following.
Okay, great, thank you. So I'm going to call, this is an example problem. We could go into it throughout today. So we have minimize j. I was going to make 3D plots. I didn't, I'm sorry, but I think the contour plots suffice. And just like much of the other information is found in Bryson and Hull's book, it's hard to find. So you can also find it in Langowski's book, and I could give, there'll be references in the typed out notes to those. So we're going to have one constraint. So this cost function is basically an ellipse, right? So you have x grid and u grid over some a and b, and that determines an ellipse, right? And then we have a line that's x plus mu minus c. So on a contour plot, I'm going to change this to gray. Okay. My lines are not straight. Okay, so we have, call this x and call this u. And then we have, these ellipses here. And then, so as we go this way, j is increasing. So this is the smallest cost function because this is 0 at the middle, and as you go out, it increases with those contours. Let me label this contour plot. Okay. And then we have this constraint 2. It actually can be anywhere, but it is kind of goes through here. So the solution actually has to lie on this line. So this is f. Okay, so then that's what this problem looks like. I'm going to use it to motivate some things later, so it's good to present it now. Okay, so today we're actually going to cover, they build on each other, the 3 methods to solve these constraint problems, and only the last one will we use in the future, but the other 2 I think provide helpful insight and kind of, yeah. So I'm going to cover them. So the first is like it's an unenjoined method, and I'll explain what that means later. And it's the first one, so I'm calling it unenjoined method 1. So okay. For an that's an ob. So for a stationary point, so that's where, it could be a minimum or maximum. This is equal to 0. For an arbitrary arbitrary du, right? So for any du, this is equivalent to what we solved before. So then we get this equation, right? So dj so we have to take into account both the change in u and the change in x. So that's 1.7. Also, for dx to change without changing f. So the idea, right, is that f is always equal to 0. So we want this, there's going to be some change to, arbitrarily, if you change x, you're going to change f. But you want it, so we only are concerned about changes in x that don't change f, so that f can remain 0. So then we get this kind of result. So it's actually the same as the cost, but in this case we care about the constraints. Okay, and that's 1.8. So we have these two systems. Then rearranging 1.8 yields so there's a requirement here that the inverse of f of x. So if you didn't catch, or I guess I meant to write out here, but I didn't. So this, so like this is this notation, is equal to j and underscore x. So I'll use those interchangeably. So solving, rearranging 1.8 grants you this here. And there's a caveat that this is non-singular, if you can see my pointer here, is non-singular. But that is necessarily the result if you pick your states and your controls correctly, so that the states are determined by the controls. Then you will
Hey, Sean.
yeah.
Just a notation question on the first term of the 1.9, the negative f, and then you have like
This
I guess the subscript x bar to the -1.
Yes.
Could you just explain that term by term? I want to make sure I.
Okay, so I meant to write this out and then I got ahead of myself. So this here is equal to, and thank you for asking, I appreciate it.
Yeah.
So this is equal to this, right? So, and these are underscores here. So like f bar with this x is the same as this. So these are equivalent, right?
Yeah.
So then we want to solve for dx. So then we take dx over here, right? And then we get, and then negative fu du, and then we multiply by the inverse of.
Oh, okay. Sorry. Yeah, I totally understand. Just got lost in the notation. Thank you.
That's okay. I skipped a step. So, yeah, so then we substitute 1.9 into 1.7. So we take this dx value and we substitute it up back in here. And so we get After this equation, I'm going to stop putting the bars in. If it confuses anyone, ask me, but it just kind of clutters the space too much. So we get this equation here, and then that, because this is, du is not equal to 0, so then this is equal to 0, right? So then, as a result, CV. Okay. So this gives us right here, and you can tell because this is a scalar with a differential of something of n values. So this gives us m equations, and then we add that to the n equations from f equal to 0, and then that's where we get our m plus n equations for m plus n unknowns, and those are x and u. Okay. So hopefully everyone followed that. Any questions?
Sean, just one addition in equation 1.8. I think we have to have a 0 on the right hand side, right?
1.8?
Like,
oh,
yeah. So D.
Yeah, it is. I'm in 1.7. You're right. Once again,
no problem.
I stopped writing before I should have, but that comes from the descriptions, right? So we have the DJ is equal to 0. Thank you for pointing that out.
No problem.
Okay.
Yeah. Good job, Sean.
Okay, so there's no other questions. I'm going to move on to the unadjoined method. Oh, I forgot my insight. So let's note this. And I actually think this has been useful for me. So I did my notes out of what I meant by. So if we look back on 1.7 and 1.8, right? As we did, is that there's a symmetry here, right? We have dj equal to 0 and df equal to 0. And of course, df is several equations, dj is just one. But there's a clear symmetry there. And this is something that's kind of bothered me for a while until I connected it. So this actually implies something. 7. So this indicates that we can interchange. Okay, let me not try to spell interchangeability, and instead just say that we can change the objective with a constraint. So, for example, where I've seen this is, say you're trying to maximize downrange for a given terminal velocity. That problem is equivalent to if you pick the optimal downrange for that value, but then try to maximize terminal velocity. Those two problems are equivalent. And you can see that because if we take like min of some fi of x and u, such that we have j minus j star, where j star is the optimal value of j from the previous problem, and then we have let's just say j not equal to I, j equals 1 through n. I know it's kind of sloppy, like not clear, super clear, But basically, we pick out Fi and replace it with J minus J star. For clarity, I'll include that. The X U and equal to 0. This is actually equivalent to the previous problem. I did forget how to spell equivalent. 2. And you can kind of see that. So if you remember that contour plot of our example, so we have the gray, but we pick the optimal ellipse, instead have like various contour lines of yellow. Right, there will be a point where these intersect, and that would be give you the same solution. So it's not super coordinate for now, and let me just indicate this is F, I increasing, right? And then J is equal to J star. And practically speaking, this is coordinate because a lot of times when people pose optimal control problems, they'll how do I say this? They get too hung up in constraints and make everything a constraint, or they get too hung up and make everything an objective, or they solve multi-objective problems. A lot of multi-objective problems can actually be avoided if you just make one of the objectives a constraint. Or if you don't want to deal with it as a constraint, you could actually make that constraint an objective. So you could kind of change things out, if that makes sense. So this is good to keep in mind for the future. And I think that the fourth method kind of really shows that. Okay, now to, where was I? Sorry, I confused my notes. Okay, yeah, here we go.
May I ask a question about the interchangeability?
Yeah.
So just to clarify, this only works for equality constraints, correct?
Yes, but as you will see at the end of today, hopefully in 15 minutes, that equality constraints and inequality constraints, the way we solve them is just, inequality constraints is just, you solve the problem both as an equality and an unconstrained problem. So, yeah, in that sense, it's true for active constraints. Let's just say that, and active constraints behave like equality constraints. Okay, so hopefully I'll try to speed it up here. So we go to unadjoined method 2. And then this is where we introduce Lagrange multipliers. So for convenience, I'm going to combine U and T. No, not U and T, U and X in one single vector, and for now I'll call that Y. And then if we look back at our contour plot here, draw it one, maybe a few more times. But now, so right, we have our concentric ellipses. Well, these keep on getting worse and worse. Right? And then we have, say this is optimal point, and we have a line in which the solution's on. Note that this point here is tangent, so these two contours are tangent to each other. So we have some gradient of F, and then some gradient of J. And you could note that the tangent, so if we zoom in here, and get some really light color, and zoom like, so right, if we have, this is a line, and say we have, intersecting here, and here's our tangency. So J is increasing this direction, and then in this direction, J is also increasing. So, right, we have to lie on a tangent, because if we say we're here, well, we could decrease J by sliding this way, and if we're here, we can decrease J by sliding this way. So, is that clear to everyone why that has to be tangent? I assume the silence means it is. Okay. So once we know that, tangency results in gradients of J and F being scalar, I guess this is Fi, poles of each other. So then, so we have like dj, dy, and that's the gradient, right? So gradient J is equal, and then that's equal to the sum, and I'm making this negative for convenience, but this is a scalar multiple, right? Of, okay. Then we can combine that together into some vector, and df, dy. Yeah, so we write in vector notation, and that's a negative. So therefore, we have the t f y is equal to 0. And then we would call lambda Lagrange multipliers. Okay. And then we could separate y. So then we have, this isn't super necessary, but it's helpful to see that here we have n equations, and here we have, if we do with u, then we have m equations. So then we have what we need. And then we get another, yeah, so then we have what we need.
I have to ask, is that J subscript Y or J multiplied by
Right
some
here,
scalar?
that's subscript. This one here.
Yeah.
Sorry. I wish I could do this on paper. My handwriting is clear on papers in this tablet. Oh.
Thank you.
That I knew we needed n more equations, then we had to solve. So let's call this. This is 1.12. Oh, actually, sorry. Solving 2 for lambda yields. So we have an expression for our Lagrange multipliers. Okay, so this is another like intuitive note to grab from this. is if we look at this, so let me write from 1.14. So these Lagrange multipliers, which, spoiler alert, become co-states. In the future, they are known for not being intuitive, but they actually do have an interpretation. So if we take above, right, we rearrange, so basically 1.14, it's just rewriting it again, but then you can see that this is the same as dx, and then this is inverse, so and this requires being evaluated at some du. But then we yield evaluated at u. So what this means is the Lagrange multipliers indicate how much the constraint affects the cost. So in layman's terms, say you have, some constraints where it's like, okay, the diameter is constrained to 2 inches, and you try and measure strength, and you get some Lagrange multiplier out. That Lagrange multiplier. What's that?
Sorry, Sean. It seems like the sign was reversed for lambda between 1.14 and 1.15.
Oh.
Is it negative JX?
It's negative. I just got the negative. Thank you for pointing that out. Negative and negative. Technically, they still work if you switch the sign, but then it just won't be consistent. But basically, the Lagrange multiplier will tell you how much that diameter how much your cost will go down or up if you increase or decrease the diameter in the example. So if you're trying to maximize strength and get some Lagrange multiplier for a constraint that is 2 inches diameter, that Lagrange multiplier actually indicates how much your strength will go up if you increase or decrease the diameter. So they do have a meaning. It's just not super obvious. We're going to get an example. I'm going to solve the example problem at the end, just because for time. Because I can always leave that for you to do yourself. But we actually only have 2 more pages of homework. Oh, not homework, notes. So almost done.
Sean,
yes.
Sean, is it okay to just add one line for the benefit of the other 4 attendees? What Sean is saying is perfect. And another way to view what he said is this, that the Lagrange, these parameters also give the indication of the sensitivity of your objective or your cost to the constraints. So sensitivity of J to F, different things that are in F. So that is another way of seeing things, how sensitive things are.
Yeah, and that's the right word to use. I should use the word sensitivity. That's it. Yeah. So yeah, that's what this is, right? The partial J with regards to F those are sensitivities. So you are right. Okay, so the last, and this is actually what we're going to be basing everything off in the future, is the join method. So because F is equal to 0, we can join, see what that means, F to cost without changing, and I guess I should specify at the solution. Its optimal value. So you'll see soon, but here lambda 1 through lambda n are not yet specified. So we're not making any assumptions about these parameters. They can be anything at all. And the lambda, that's all, because they end up being Lagrange multipliers. But right now, we don't know anything about them. We just get some augmented cost functional. So x of u is equal to j. So the prime I'm using is to specify that it's augmented. It's equal to 1 I to f of I x and u. Then this augmented cost. Okay. And then this, we can make this into vectors for convenience. Plus lambda t of f. Okay, so then, and let me call this 1.16. So, like you could expect, we concern ourselves with differential changes. So differential changes in j prime are dj prime. As you can expect, the partial j with respect to x dx plus partial j prime with respect to u du. 1.17. Okay, so we are fundamentally concerned about how the changes in u affect changes in d prime. So that's like kind of why we set one as control. So now we can take this step. So we pick lambda to eliminate dx, so the dependency in x. So basically, right, we have this here. We want to eliminate this portion here. We're going to take that out. To do so, we just set, we say j prime x is equal to so this is the simple partial. So we want this partial here. So for any dx, we want this to be 0. So we want this partial j prime, partial x to be 0. So we take the partial j prime with respect to x. So then we get the partial. That's the partial of j with respect to x plus lambda t partial f of x partial x. So that's just kind of, applying it here. So we just apply the partial through, and we want this to be equal to 0. And since lambda is not specified, we could specify lambda to make this equation 0. So that results in lambda prime is equal to negative. And look at how fortuitous this is. It's the same as it's the same as 1.15, right? So just if we set this so that this is equal to 0, this ends up being the same as 1.15. So they are indeed Lagrange multipliers. So we plug in 4 prime du. So this now looks like the unconstrained problem, right? Which is kind of sweet. So this is equal to u. So this augmented cost functional acts like the unconstrained problem. And then, so, salting. So this equations J prime and this is M. So we have 2n plus m equations, and then we have 2n plus m unknowns. And where we got the other n unknowns are the Lagrangian multipliers. So this is x, lambda, and u. Okay, any questions? Okay, so then I will, I'll circle back to the example, and just do problems with inequality constraints. Oh, my handwriting's getting worse. Okay. So, I need to remove that line. So then we kind of redundant, but problems may also contain constraints of the form g x of u is less than or equal to 0. We only concern ourselves with this kind of form. Obviously, you could consider greater than or equal to, or some kind of bounded, but you could re-express using negative signs and pulling things apart, every inequality constraint this way. And then in practice, you're not going to get, posing a problem without a less than or equal to doesn't really make sense. Because if you just say less than, that means you could get infinitely close to the boundary, so it's practically the boundary. So it's always going to be less than or equal to in this case. Really, and we don't lose any kind of generality with only dealing with that. So there are two cases. That can exist, and this is kind of what I referenced earlier. We have the first one where the particular constraint is inactive, which means that the solution is not on the boundary, constraint boundary. It also means the choice of x does not depend on u. And then in practice, in a way, if you have problems where this is true, it's kind of silly. And maybe you're solving a lot, so then it doesn't matter. and you're just posing it generally. But if the constraint's not active, then you get the same solution whether you have the constraint there or not. So that's a simple. My little writing pen's like melting in my hands. So it's kind of getting sloppier. Sorry for that tangent. So we have this constraint here in this function, right? In the optimal solution. So everything can't be left of this line. The optimal solution's here. If we take that constraint away, the optimal solution is still there. So those can be solved. If you know the constraint's inactive, then you can solve it like a unconstrained optimization problem. Then we go to active, and then it's, you know, the opposite of before. So is on the constraint boundary. And then the constraint can be treated as a equality constraint. So then a little 2D example here. Have this. And some kind of function like that, and then the optimal is here. And put like U star. Okay. And then the last thing to know about this. So basically the way, there's other numerical methods and other ways to address these kind of inequality constraints. The simplest way is you just iterate through the different possibilities. So you solve the problem as if it's unconstrained, and then you solve the problem as if it's constrained. If you have multiple constraints, then you combine all combinations of those, and then you find which one's the minimum out of those. It's kind of tedious, so that's why there's other methods to do so. But that's kind of what you get. But hopefully you could use you'll plot it and get a better understanding about the shape of the function. You could kind of use intuition to seeing what's active and inactive. This kind of problem of like when the inequality constraints active versus inactive actually comes up later in this course when it's in dynamic systems, and that's why Hitch has developed like UTM, because it really makes this a lot easier. But that's just a taste of what we have. Any questions? Okay, if not, I guess I will, how about I try in the next 10 minutes to solve the equality constraint example, and then I can give either here or send it out in inequality constraint homework thing. Exercise.
Sounds good.
Okay, so going back.
Yep, that sounds good.
Yep. Okay. I just had to find where I had the solution. I'm kind of old school. I'm juggling all these pieces of paper on my desk. Okay, there we go. Cool. Yeah. Cool. I complained about my pen and then I actually broke. Luckily, I have like 10 of these S pens, so. So, going back. So we minimize J is equal to, and this is what we're shown before. This one actually writes better. U squared plus U squared. And that's such, subject to f of x u equal to x plus mu minus c is equal to 0. And then everything that's on x and u is constant. So let me just write that out. Yeah. A, B, M, and C are constants. So let me write the concept plot one last time. Let me have some, this is super sloppy. We have some line, this is F, and then this is J, which goes up this way from 0. And then we expect to see an optimal solution here, but since we're not working with numbers, you can check that in your later. But so we have a cost, we augment it. So J prime is equal to J plus lambda F, which in this case is equal to, in of all the methods, this third one is by far the easiest to write out. Times X plus U C. Okay, so that's our augmented cost. So we take partial J prime, partial of U, and that's equal to U B squared plus lambda M equal to 0. Right? So U cancels 2, B squared, lambda M is equal to 0. And we take the same, but with respect to X, that is X over A squared plus lambda is equal to 0. Right? So 2 over A squared. Right? And then we have the final one, which is F is equal to X plus mu, and this is our constraint. So we have 3 equations for 3 unknowns. And then we basically just solve this. It's just solving a linear equation. Then we get X is equal to squared C. So that's equal to MC A squared. And while preparing these notes, I solved this problem with the other two methods, and the math is a lot not as nice. So this is by far the preferred method for this problem, and it's a preferred method for Beluga. Okay, and this is a minimum. You can check it by taking the second derivative, but the reason why we stop paying attention to second derivatives is they come up later to prove optimality. But if you have most trajectory optimization problems, there's a rare exceptions where you can come across a maximum instead of a minimum. For most cases, the problem that you pose, you're going to get a minimum. Because maximizing terminal energy, it's really easy to, if you get something that looks like it's maximizing terminal energy and not just kind of like floundering, then you're doing it. So there's not much to worry about there. So in most cases, we just care about fourth order conditions. Okay, that's all that I have. I'll send out the other problem and then a solution. I'll send them in 2 different PDFs. That way you can do the problem and then you can check the solution.
Are those denominators a squared plus m squared plus b squared?
No, for u is a squared plus m squared b squared. It's
times b squared.
times b squared.
Okay, for u.
But for x, it is added, right?
If any of you have Bryson and Holt, it's added. So let me actually check because I was looking off notes on that I copied. So it is x is a squared c over a squared plus m squared b squared. Oh, so I miswrote that. This is no plus here. And then this is the same, a squared. So the denominator for both of these is a squared plus m squared b squared. And then this one is, this is no, oh, and then I forgot the b squared here. Okay, so all the denominators are a squared plus m squared b squared. And then you have...
And that includes for j as well?
J is 2 times a squared plus m squared b squared. I must have miswrote these notes when I really miswrote the notes when I took them back in years ago. So that was a mistake long coming.
All right. Well, thanks for the lecture today, Sean. I really appreciate it.
Oh, thank you.
Sean, can I add one fun fact?
Yeah, you can add as much as you want.
Just a very short fun fact for the other people in the audience, that Sean very well said that we don't go to the second derivative in general, and that is what mostly we used to do in our previous lab as well. But then I encountered a mass arrow capture problem in which I was getting exact opposite solution. Like I was looking for a minimum, I was getting a maximum. So it may happen very rarely that you might find some problems like that, but just heads up that there might be situations where you might find that case.
It's funny, that's the only problem that I've ever heard it happening on, because I was trying to think of problems, and it was that arrow capture problem that I heard talked about. So
yeah, exactly. That one was brutal.
All right, good stuff. I look forward to hearing from you again on Friday.
Thank you. I'll talk to you all later.
All right. Thank you, Sean. Great job.
Thanks, Sean. Great job.